Hello students, happy Monday. Today we're going to cover 5.5. Right now I'm actually looking at some stuff from 5.4, so I want to quickly talk about what we saw last class. Last class, for the first time, we saw a sampling distribution of sample means. So in this example here on page 1, we took random samples of power forwards, MBA power forwards, and then for each of those random samples, we calculated the sample mean, and then we plotted on this plot. So each and every one of these points here represents a sample mean. And we saw that the resulting sampling distribution has a few specific characteristics. One is it's the shape of it sort of inherits some characteristics of the shape of the population. So if the parent population is approximately normal, then the sampling distribution of the sample mean will also be normal. Also, the mean of the sampling distribution of X bar is just equal to the true mean, whatever that is. So this is how we find the mean. The standard deviation, we have this nice formula, which is that the standard deviation of a sampling distribution of sample means is just the true sigma divided by the square root of n. Okay. We also saw, again, so to a certain degree, the shape of the sampling distribution of X bar takes on characteristics from the parent population. In this other example where we're looking at shooting guards, the parent population of the shooting guards was left skewed. It kind of looked like that. And we can see that when we take very small samples, so in this example, we were taking samples of size n equals 2, we can still see a little bit of that residual left skew. But if we take big enough samples, so in this one, we were taking samples of n is equal to 10, it starts to look more and more normal. And indeed, we have something called the central limit theorem, which says that as long as we're taking big enough samples, we are guaranteed to have a normally distributed sampling distribution regardless of the shape of the parent population, which is a very, very, very powerful theorem. One of the most important things we learn in Unit 5, to be honest with you. How big is large enough? Well, we use n is greater than or equal to 30 to be safe. So again, last class, sampling distribution of X bar. It's going to be normal if the population distribution is normal or as long as we have a big enough sample. The center is just equal to the true mean. The standard deviation is equal to sigma divided by the square root of n. Make sure you check your 10% condition when sampling without replacement. All right, let's go now to 5.5. So I'm at the top of page 6. Okay, 5.5, sampling distributions for a difference of sample means. It says, over 1,000 students at East Kenwood High School have taken the AP Stats exam. The distribution of scores is approximately normal. Okay. So, excuse me, the distribution of scores is skewed left with a mean of 4.09 and a standard deviation of 0.83. At Rival High School, the scores are approximately normal with a mean of 3.07 and a standard deviation of 1.12. Okay, we're going to randomly select 40 students from EK who have taken the AP Stats exam and 20 students from RHS who have taken the AP Stats exam. And then it says, use this information to describe the sampling distribution of the average AP score for each school. So we're going to start by just considering the two separate sort of underlying distributions here. So we're going to start by just considering a one sample situation. And what do we know to help us do this, to determine the shape, mean, and the standard deviation for each of these subpopulations? Well, we know that the shape is going to be approximately normal if one of two things is true. Either one, the population distribution is approximately normal, or two, we have a sample size that's at least 30. A large enough sample size would do the trick as well. Okay, what about the mean? Well, we have this formula for the mean. The mean of a sampling distribution of sample means is just equal to the true mean, the parameter mu. And what about the standard deviation? We have this formula. The standard deviation is equal to sigma divided by the square root of n. So, okay, for EK, it said that the parent population is skewed left. But we're in luck. We're taking large enough samples. So what we can conclude is that the shape of the sampling distribution for EK will be approximately normal, because the sample size is large enough. Okay, 40 is definitely greater than or equal to 30. So then this satisfies the central limit theorem. Okay, what about RHS? Well, for RHS, they told us that their scores are approximately normal. So we're guaranteed that the sampling distribution for RHS will also be approximately normal, because the population distribution is approximately normal. So it does not matter how big our samples are. It doesn't matter that we're only going to be taking samples of size 20 from RHS. We could take samples of size 2. It would still be normal. It's guaranteed. Okay, what is the mean of the sampling distribution for EK? Well, it's just going to be equal to 4.09. That is the parameter given to us up there. What is the mean of the sampling distribution for RHS? Well, it's just going to be equal to 3.07. Again, that's the parameter. It was given to us right there. What about the standard deviations? Well, we have this formula. In this case, we have 0.83. That was a standard deviation given right there, divided by the square root of our sample size of 40, gives us a standard deviation of 0.131. One more time. We're going to use the formula. Sigma for RHS is 1.12, divided by square root of the sample size, which is 20, is going to give us 0.250. Okay, so this is what the individual sampling distributions look like. But this section is called sampling distributions for difference of sample means. So we're about to start subtracting. So down here in the next part, what does it say? It says, suppose we took a simple random sample of 40 students from EK and a simple random sample of 20 students from RHS and found the difference in the sample means. Describe the sampling distribution of the difference in mean AP scores, EK minus RHS. Okay, so here we're now taking two samples and we're looking at the difference. What is the shape going to be of this distribution of sample differences? Well, it'll be approximately normal. Because each of the sampling distributions above are approximately normal. Okay, that was true when we did differences of proportions too. It's like as long as the two subpopulations are normal, then we're guaranteed that the sampling distribution of differences will be normal as well. What's the mean? What's the mean going to be for the sampling distribution of sample differences? Well, what are we going to do? What does it look like to do this? I mean, we're going to take a sample from EK and then get the mean of that sample, and a sample from RHS and get the mean of that sample, and then subtract those, and then graph the difference on a dot plot. And we're going to do that thousands of times to make our sampling distribution. Where is that new sampling distribution going to be centered? Well, it's going to be centered on the true difference between these two populations. In this case, it'll be centered on 4.09 minus 3.07, which is 1.02. And indeed, in your formula sheet, you have this formula, which says that the sampling distribution of sample difference, the mean is just the true difference of the means. What about the standard deviation? Well, okay, you should be thinking to yourself, I can't subtract standard deviations. I know better than that, okay? Never subtract standard deviations. And I also can't add standard deviations. I know better than that too, because of the Pythagorean theorem of statistics. What can I do? Well, we can add the variances and take the square root of the variances. Again, it's the Pythagorean theorem of statistics back again. So the variance actually looks like 0.83 squared divided by 40, okay? Because remember, like, the formula for the standard deviation in this case is sigma divided by the square root of n, but the variance is a standard deviation squared. So we end up with sigma squared, and then this square root goes away, and so we just have n there. Plus 1.12 squared divided by 20 gives us 0.282. And again, this formula is in your formula sheet. In the formula sheet, it looks like this. Okay, well, what do we do with this? What's the point? It says calculate the probability that the random sample of 40 EK students has a higher mean AP score than the random sample of 20 RHS students. Okay, let's draw a picture. So this represents our sampling distribution of differences. It is centered on 1.02, the true difference in means for these two populations. Okay, where higher? So what we want to see is that EK, the mean for EK, is higher than the mean for RHS. For one thing, the direction of subtraction matters a lot. We're subtracting EK minus RHS. So anytime that the result of this subtraction is positive would indicate that EK was having a higher mean. In other words, what we need to look at is everything above 0. So 0 is going to be our lower bound, and we're going to be looking at everything above 0. Again, why is that? Well, it's because this is the region where EK is bigger. Down here is the region where EK would be smaller, okay? This is why keeping track of the direction of the subtraction is very important. So I want to know, solve this problem. What's the probability that the difference of the sample means is greater than 0? Okay. Now it's just down to a little bit of normal CDFing. We have a lower bound of 0. We have an upper bound of positive infinity. Our mean is 1.02. Our standard deviation is 0.282. Okay, we calculate the standard deviation here. And we end up with 0.9999. It's almost 100%. It's almost a certainty that any given two samples will have a higher sample mean for the RHS students for the EK students than for the RHA students. Okay, let's take the important notes at the top of the next page, and then you'll have a chance to try a problem. So, what did we learn about? We learned about how sampling distribution of the difference of a sample mean. We learned how that functions. So, thing one, the shape. Okay, the shape is going to be approximately normal if both sampling distributions, so both of the sub-sampling distributions, x bar 1 and x bar 2, are approximately normal. By either 1, they have a normal population distribution, or 2, n is greater than or equal to 30. Okay, what about the center? We have a formula for the center. The mean of a sampling distribution of the difference of sample means is just equal to the true difference in the means. And what about the standard deviation? Okay, again, we have this formula. The square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. And then my final thought here is just, we still need to be checking that 10% condition. So check the 10% condition anytime that we are sampling without replacement, which is most of the time. All right, that's all I got for now. You are about to try this check your understanding problem right here on page 7. Feel free to leave this video paused for people to kind of finish writing for a moment, and I will see you in the next one. Goodbye.